Probability and statistics, the probability functions. This is dealing with some terminology, a bit of theory with some calculations. Discrete random variables. What do we mean by discrete random variables? Well, discrete means having only particular values, numeric, and part of a finite set of numbers. If we're selecting a committee from 1,000 students, then it's a finite number. We can say exactly how many. Set number of outcomes. For example, if you roll a die, you can only have 6 outcomes, and that is discrete. Random means that a variable is not part of a pattern, a selection, and equal chance of being chosen as any other variable. If you watch a lottery being drawn, that's usually done with a barrel with balls inside. The balls are all the same size, they're the same mass, everything. The only difference is their color and the number on them. And they supposedly have equal chance of coming out as any other ball. Dice rolls are used in experiments sometimes to choose randomly. We draw a number out of a hat if it's a little local competition. Adding all the probabilities of the random variables, all of them within an event, must give the sum of 1. We've already established that. Sigma I equals 1 to n pxi. So px1 plus px2 plus px3 to pxn is 1, or the sum of all x, little x, where p, that random, discrete random variable, is equal to the values that little x can take on, is equal to 1. An example, 3 coins spun, number of heads recorded. We're going to use capital letter X, in other words, the uppercase to represent this variable. Any capital letter, uppercase letter can be used. What's the possible values that X can take on? Well, we're spinning 3 coins. So 0, 1, 2, or 3 is the number of heads we could obtain. Those are the little x values, and the variable big X can be equal to any of those little x values. By the binomial distribution, the binomial formula, and if you don't know the binomial distribution, I would suggest that you first go back and look at the video in this series on the binomial distribution, because this does assume some knowledge of it. And there's also the hypergeometric distribution, which you should look at, because that's also referred to in this video. By the binomial distributions, there's the sum of all probabilities, the sum when we have the variable x equaling 1 through to 0 through to 3. They're the probabilities by the binomial distribution formula. There they calculated, and to confirm these formulae, definitely it's equal to 1, because those are all the probabilities, those are all the different outcomes that can occur in this event. Probability mass function, the PMF, gives you probabilities for discrete random variables. So it's a function, as opposed to the probability density function, the PDF, for continuous variables. Continuous variables are things such as mass, people's mass, because if I said to you, how many different masses are there between 10, let's say 60 kilograms and 70, you could not give it, because they're decimal places, all sorts of things. It's continuous. Properties of the probability mass function, f of x, there's the probability mass function, is equal to the probability of this variable, the discrete random variable x, equaling any particular values which little x can take on. Little x is like the n in the sigma notation. Some properties. First of all probabilities are non-negative. Notice it doesn't say positive, because 0 can be included. Any event in the distribution, such as scoring between 20 and 30, has a probability of between 0 and 1. 0% to 100%. The sum of all probabilities is 100%. An individual probability can be found by adding up the x values in that event A. So, for example, we might say we throw 2 dice. What's the probability of obtaining a sum of 8? So we say, well, what x values within all the different possibilities will give us a sum of 8? Let's look at an example. A coin is biased to make the probability of spinning ahead a quarter. Interesting coin. Find the probability distribution of the random variable x, the number of heads obtained when spinning the coin 3 times. So we've already had that. There we are, 0 to 3. Now we have to find the probability distribution. When you find the probability distribution, you have to give the probability of every one of the discrete outcomes. So there's a table, and we can use the binomial formula to calculate each of those probabilities. Remember, binomial is probability of only two possible outcomes, success or failure. Success would be spinning a coin, tail would be not spinning a coin. So the probability of success when we're looking for 3 coins, 3 heads, it's a probability of success cubed and failure to the 0. And that's a number of ways it could be arranged, that combination, which works out as 1. And so we go through the different substitutions into the binomial formula. A distribution can also be written as a mapping, shown as a mapping. There we are, algebraic mapping. 3 is mapped onto 64. So the value of x3 is mapped onto the probability of 1 over 64. Every input has exactly 1 output, and that makes it a function. Right, there are 2 inputs going to the same output, but the important thing for a function is that no input goes to more than 1 output. So the function describing the relation between the discrete variable x and its corresponding probabilities is the probability mass function. So here is the probability mass function going on to obtain these outcomes. Other ways we can define a function in statistics, similar to algebra. There's the table, which we've seen, mapping, which we've seen, graphically. So here we are, 0 heads, the probability is 3 of those 6 portions, which is a half. We can do it as a listing, and that's okay to do here because it is a discrete. There's a finite number of outcomes. And we can do it as an algebraic expression, which is used more often for when they're not discrete, when we have the probability density function. This isn't related, these all relate to the same question earlier. This is just some other one. I was going to say some random one, but I thought I better not call it some random one because I might be questioned about that. That's just a thumbsuck, that example there. So let's look at the probability distributions. Sometimes you're given the actual function. In this case, we work with the functions and the fact that sum of probabilities is 1. That sum of probabilities is 1 is very useful. It helps us form equations often to find out unknowns in the functions. So an example, probability mass function is given by the formula P x equals x is k into x plus 4 for values of x 1, 2, 3. So we have to find the values of k, a value of k, and the probability distribution. For the value of k, we're going to use the fact that the sum of probabilities is 1. It's finite. There are only 3 possible values of x, so I'm going to take probability 1, 2, and 3 is equal to 1, added together. The actual probabilities we could obtain because I just take the 1 and substitute into there, and I get my 5k. 2 into there gives 6k, 3 into there gives 7k. They must equal 1. which means I can solve for k. Now, for the actual probability distribution, I'm now going to find the actual probabilities in each case. There we are. So I'm now taking 1 over 18 times x plus 4 and out the various values. There's the distribution. Finding the probability mass function. So, as with algebraic, finding an equation, we need to find a relationship between the values of x and the probabilities, the values of x and y as such. Very similar to finding the general term of a sequence. There we are. If you have a look at this, there is the one there. Notice the pattern 4, 5, 6. So therefore we've added 5, 6, 7. We've added 4 on, 4 on, 4 on. So x plus 4 over 18. I don't know if you noticed, I've just realized this actually originally said 5 over 16. Just careless error. It's my age. But it's corrected. It's like poetic license. When you're making the video, you can just chop and change. So there we are, the relationship. 1 plus 4 is 5, 2 plus 4 is 6, 3 plus 4 is 7. So we know it's x plus 4 all over 18, so x plus 4 over 18. Only the values 1, 2, 3, and therefore the probability is 0 for any other value. So an example, find the formula for the probability mass function for the data in the table. There we are. Now if you have a look at this, you'll see that they're all over 34, so I can concentrate on the numerators here and say, well, what's the pattern 2, 5, 10, 17? That's a sequence. First difference 3, 5, 7, second difference 2, common second difference, so it means it's actually a quadratic sequence. And if we use your knowledge of quadratic sequences, you end up with Tn equaling n squared plus 1. So there's the formula for 2, 5, 10, 17. So that being the case, we can substitute x for n, little x for n, and we know that the probability of x equals x squared plus 1, there's the n squared plus 1, x squared plus 1, over 34, don't forget we're just working with the numerator. X equals 1, 2, 3, or 4, and 0 if x is not those values. Special probability mass functions. Here we're going to look at the binomial and the hypergeometric mass functions. So just a reminder, binomial distribution when, first of all, each event of the process results in one of two possible outcomes, being success or failure. Probability of success is the same for each event, and the events are independent, meaning that success in one event does not influence the probability of success in another. If you spin a coin and you get the head you want in the first, the probability of a head does not change for the second spin. So an example, 9 dice are thrown and the number of 3s is recorded. Find the probability that the number of 3s appearing is, well, 4 options, 1, then 2, then 6, then 9. So, it's binomial because we're looking at number of 3s, so what we're interested in is 3 or not 3. 3 or not 3, so success, failure. And there's the definition of the binomial distribution in this case. Binomial, 9, because that's how many we're choosing from, the n, and little p means the probability of success. So there is our formula for the binomial distribution. Number of successes, little x, number of failures, n minus x. In other words, we've thrown it 9 times, so however many successes, we'll get 9 minus that number failures. This is the actual probability of success, which in this case would be 1/6, because you have 6 different options in throwing a die, and probability of failure, which will be 5/6, 1 minus p. There we are. So there's our binomial formula. There we are. nx, so 9, 1, and that becomes 9 factorial over 1 factorial, 8 factorial. There's your p, there's your q, which is 1 minus p. 1, because we're looking at probability of getting 1. And there's the calculation. There's probability of 2, same formula. Pause and try 6 and 9 yourself. Right, probability of 6, 0,001, hope you got the same. And probability of 9, pretty small chance of getting 9 3s. Yet some people will bet on it. Now let's look at the hypergeometric mass function. A reminder, the difference, we use hypergeometric distribution when the population has 2 or more types of objects. So that's already different from the binomial, because the binomial can only have 2, success or failure. This one can have more than 2, it can have any number of objects. It just means we have to allow for each in the formula. A sample is chosen without replacement, so no replacement, and that means the events are dependent. The probability changes with each selection. When I choose a king from a pack of cards, that means the kings are 1 fewer and the cards in the pack are 1 fewer for the next choice. Example, a class of 30 people consists of 12 boys, 18 girls. Committee of 5 is to be chosen from the class. Find the probability mass function for the number of girls on the committee. So there are 6 answers we need. 0, 1, 2, 3, 4, or 5 girls on this committee of 5. Those are just for the formula which is coming up. This can be done. You don't have to remember the formula. This can be done just by logic and using the principle that you multiply the number of events together. If the chances of getting A are 5, the chances of getting B are 6, then the chances of getting A then B is 5 times 6. It's called the counting principle. So N, the size of the population, 30 pupils. Little n, the size of the sample, well, there are 5. R, the number of successes in the population, well, because we're choosing girls, we're asked about girls. 18, the girls are the success, so 18 is the answer for R, and 12 is the number of failures. R is the number of successes in the sample, well, that's the variable that's going to change. And n minus r, the number of failures in the population. So 30 minus 18 gives you 12. We do it that way around because there might be 3 options in a question. There might be more. So now, we're going to do it logically. What we're going to do is we're going to say, well, in how many ways can we choose? If we're doing, let's say, 3 girls, we're going to say, in how many ways can we choose 3 from 18? There. Times, and how many ways can we choose the remaining 2 from 12? There. And we divide by the total number there. So let the number of girls be x. There's our discrete random variable. Number of success in the population is 18. Number of failures is 12. Sample size 5. And it's chosen from a population of 30. So x can have those values, which means the failures, number of boys, are those. You subtract 5 minus 0, 5 minus 5. So now, number of ways in which one girl can be chosen from 18, because we're having one girl, so it's 1 from 18, which is a combination because order does not matter. Number of ways we can choose 4 boys from 12, so it's a combination because order doesn't matter. That's where we get that combination for choosing one girl from 18, and we choose 12 boys from 4 boys from the 12. And of course, total number of outcomes. So there we are. One girl from 18. So to get 5, we need 4 boys. We're choosing from 12. Total number of outcomes is 5 kids from 30. So there's our probability. And we multiply by the counting principle. This is all covered in the hypergeometric distribution video in this series. That can be entered straight onto the calculator there. In fact, we can enter it onto the calculator. We don't need to show that. And we get 0,0625, the probability of there being one girl. Now, we're not going to go through that for all of them because that'll just make this video too long. So there are all the different probabilities calculated in the same way, showing their calculation formula. We'll put it into a table, and there's our probability mass function for the number of girls on the committee. Let's do a little check to see that it works. Remember that those are all the possible options, and therefore they should add up to 1. And they do, so it's a good check. We've made sure we haven't made any error anywhere along the way with the calculation. Continuous random variables. Now we're looking at the PDF. Continuous random variables, measuring weight within a certain range, measuring the amount of petrol put into a petrol tank, or measuring the height of people. Those are all continuous. A continuous variable is a variable that can be of any value in a certain range. So the discrete variables are like the counting numbers, integers. Well, counting numbers, we can't have negative in this case. And the continuous variables are the real numbers, in fact, from above or equal to 0. Note that in the same way that a point takes up no space on a line, you can fit an infinite number of points between two other points as close together as you like. Then in the same way, there's no space in a point. And being no space in a point means that a continuous variable has 0 probability for any particular value. It can only have value over an interval. We cannot say there are 30 people here. What's the probability that somebody weighs 68.4 kilograms? We can't do it. We could say, what's the probability that somebody's weight lies between 64 and 70 kilograms? That's different. Means that these are all the same. The only difference between these is whether they're equal to A and B or not. And they're all the same because the probability of A and probability of B are 0 anyway. The probability of this continuous random variable is represented as an area under the normal distribution curve. Now this is the standard normal distribution curve, which has an area of 1. Area under the curve can be calculated by using integral calculus. The integral, definite integral a to b of f of x dx. So as with probability mass functions, probability density functions must follow conditions, satisfy conditions. Non-negative. All add up to 1. And it can also be defined using algebraic expressions or a graph. We can't use a mapping because we have to show an infinite number. Let's do an example. Probability density function of a random variable x is given as kx for x between and equal to or equal to 0 and 2, 0 otherwise. So now we have to find k. And which factor we're going to use? The very one that says that the probabilities must add up to 1. Now nothing there, so the probabilities of all the probabilities of x being between 0 and 2 must add up to 1. And remember, we're going to use the fact that the probability is the area under a curve for continuous. Since x is a random variable, the sum of probabilities is 1. So therefore, the definite integral from 0 to 2 of kx dx must equal 1. Integrate, substitute your values and solve for k. This is done with an assumption that you've done integral calculus. Try the second one yourself. The probability that 1 is less than or equal to x is less than x less than 2. Remembering that the probability is related to the area under the curve. We now know half is k, see? So we now have the probability density function is half x. Right, so what we did is we said integral from 1 to 2 of half x dx. We integrate, substitute, and the answer is 0.75, 3/4. That's x is between 1 and 2. And so now the continuous random variable is given by the function 0.2 minus 0.02x. Find probability x less than or equal to 4 and the probability that x is between 2 and 6 inclusive. So being under a curve, we're going to find the area from 0 to 4. So it's the integral from 0 to 4 of the continuous random, the property density, the density function, the probability density function. There's the function. Integrated, substitute. So 0,64. Probability between 2 and 6. So we're going to do integral from 2 to 6. Here it is. And we substitute, and there is the probability from 2 to 6.